So yesterday, what we were doing was simplifying trig expressions. Today, we're going to take that idea just a little bit further, and we're doing what is called trig proofs. So you can write trig proofs on here. So a trig expression that needs to be simplified and a trig proof that needs to be proven are different in basically by one way. And the only difference is when you have a trig proof, there's an equal sign, and you already know what the final answer is, and you're just trying to get to that final answer, okay? So what we have here is a bunch of different equations, and they are saying these two sides are equal to each other. Your job is to prove it, okay? These are not equations, really, they're proofs. So I can't add something to the right side, I can't divide over to the right side, I can't subtract over to the left side, I cannot move things back and forth, okay? I am taking one side of it, I'm going to manipulate that side and simplify it and show that it equals the other side. I am proving that one side equals the other, okay? No multiplying back and forth, no dividing back and forth, only taking one side and working with that one side, okay? The strategies that we learned yesterday are going to be just as important today. So that's why we started with yesterday. In this assignment, the problems start off really, really easy, and they get more difficult the further you go. Okay, so the plan for the period is we're going to start at the beginning together. We're going to go until you guys get tired of doing the problems together and you just want to work on your own, and then we'll just see how many problems we get done. Okay, that's the plan for today. So the one thing that makes today different from yesterday is that since we have a left side of an equation and the right side of the equation, the way that we pick which side to work on is we pick the complicated side. Because we always want to simplify. We want to take a complicated side and make it more simple. We do not want to take a simple side and try to complicate it. Okay, that's a much harder process. All right, so we're going to start with number one. This one says cosecant theta times cos theta equals cotangent theta. And this is a pretty simple problem. But if you look at the problem, which side is just a little bit more complicated? The left, okay? So we are going to leave the right side exactly the same throughout the whole problem, okay? We're going to work with the left side. What is a substitution that we could make? Yeah, we could take cosecant, and we could say that it's 1 over sine, all right? So I'm going to take this, I'm going to write cosecant as 1 over sine. So I have 1 over sine multiplied by cos, and I am not messing with the cotangent theta. That's going to stay all the way through the problem. All right, what do I have on the left side now? I have cos over sine, right? When I multiply those two things together, that gives me cos over sine. Okay. And what is cos over sine? Cotangent. So cotangent equals cotangent. I proved that the left side and the right side are the same thing, and so that means I'm done. Okay, so there's not a point where we get a final answer and we put a box around it and say, oh, that's my final answer. Because if that's the case, we could just do every single problem in 10 seconds and call it good. We already know what the final answer is. The purpose of these is for you to do the proving of showing that this can be manipulated down to become exactly the same thing as the right side. That's the purpose of the problem, is the proof itself. Okay, go ahead and write number 2 on your paper. We've got secant theta sine theta equals tan theta. And I'm going to give you guys some time to do that one on your own. It's very similar to number 1. All right, so number 3 says 1 plus tan squared of negative theta equals secant squared theta. So when I look at this, I'm a little bit tempted to look at the Pythagorean identities, but it does not match up perfectly. You guys see that? I can't work with the right side, or I shouldn't want to work with the right side because that's the simple side. I don't want to complicate it, okay? The left side is more complicated, so this is the side that I want to simplify, but it does not match up with the Pythagorean identity, okay? So what I'm going to do is I'm going to use what I know about what this notation means, and I'm just going to rewrite it. I know that this notation means that tan of negative theta has been squared. That's what it actually means. And we haven't used this identity yet, but it's on your sheet. Can anyone find it? So there are these identities right here, the even and odd ones. If you guys remember back to the first or second unit, we learned about even and odd functions and what happens when you plug in a negative. So when you take tan, if you plug in a negative, the result is that you get negative of tan. Okay? So what I'm going to do is I'm going to make this substitution right now. So I'm going to say that still equals secant squared. I'm going to say I have 1 plus, and I'm taking this out and I'm replacing it with negative tan theta squared. And what happens, sorry, did you have a question? Yeah. What happens if we do a negative tan multiplied by a negative tan? Positive tan squared. So that gives me 1 plus, and now I've got positive tan squared theta equals secant squared theta. And now what can we use? The Pythagorean identity works now because now it looks right. So now we can just look at the Pythagorean identity. We see that 1 plus tan squared does equal secant squared. And since we have gotten down to secant squared equals secant squared, we have completed the proof. Okay? All right, so for very, very similar problem, go ahead and try that one. All right, so let's go ahead and write down number 5. We've got cos theta times tan theta plus cotangent theta So which side is more Did you go to the bathroom and get something to eat? Why are you chilling? Yes. We're going to work with the left side because the left side is more complicated, right? So to work with the left side, and I would say often the left side works. A lot of people kind of default to the left side because it's the first thing you see. But they typically do write the problem, so the complicated part is on the left. So what could we do? What is a strategy we learned yesterday that could help us with this problem? We could distribute. What's another strategy we have?
Can you do
Sine and cosine, yeah. So one strategy we learned was we can distribute. Another strategy we learned is that we can turn things in terms of sine and cosine, okay? So those are 2 strategies. I'm going to talk about them first, and then you guys can help me determine which one to do, okay? So if we distribute, we're going to have a cos times a tan plus a cotangent times a cos, okay? And that's going to be a little bit messy because after that we're still going to have lots and lots of functions, different functions going on. So after that, we'll probably do sine and cosine, okay, and see what we can cancel. If we work with the inside first and turn these into sine and cosine first, we can kind of simplify these to begin with, and then we can bring the cos into it. They're both mathematically appropriate. Like, you can do both of them, okay? That's not an issue. It's just that some might be easier than others, okay? So I would say probably the easier way would be to deal with the inside of the fraction first, and then bring the cos into it after, okay? So both valid options. When you're doing these proofs, there's infinitely many ways to get them. It just might be some of the ways are way harder than the other ones, okay? So what I would do first is I would take this and turn it into all sines and cosines. So we're going to say tan is sine over cos, and cotangent is cos over sine. Good. And when we have two different fractions and we want to add them, what do we do? Common denominator. So this one has a denominator of cos, this one has a denominator of sine, and that means that the first fraction would need what? Sine. So we're going to do sine on top and bottom. Okay? The second fraction has a sine, so what does it need? Cos. So it's cos on top and bottom. Okay. So we keep the cos out front. We now have that common denominator of cos and sine being multiplied. And what's the top of the first fraction? And what's the top of the second fraction? Cos squared. Okay. So once you get that, what do you see on your sheet? Yeah, sine squared plus cos squared equals 1. If you look at your Pythagorean identities, that's like the original one. So we do have sine plus cos squared equals 1, so that means this whole thing cancels out and leaves a 1 behind. So I've got cos theta times 1 over cos theta sine theta. Because if you look at your sheet, sine squared plus cos squared equals 1. Okay. Anyone see what we could do next? Yeah. Yeah, so if we think about multiplying these, we are multiplying by cos, here is dividing by cos, so that means they can cancel, right? And so we have 1 over sine equals cosecant. And those are the same thing, right? 1 over sine is cosecant. So now we can say cosecant equals cosecant. I made them exactly the same, and so my proof is done. Yes, ma'am?
So basically, when you basically, you see how cosecant is 1 over sine. You just got to prove that the left side is the same thing.
Mm-hmm. So your goal in this, you are not solving an equation. You are proving that one side is identical to the other. And so what we're doing is all the substitutions and legal math moves we can until we can simplify this side down and show that it really was the same. Okay? All right, so go ahead and try number 6. Yeah. So what I'm going to do in a testing situation is these ones, the sum and difference, double angle, and half angle, these ones are like the really funky ones. These ones I'm going to put on a little half sheet, and you'll get this with your quest or test or whatever we end up doing. Okay, you'll get these ones for sure. These other ones, you'll start to realize that like you're kind of memorizing these, like you're starting to get more comfortable with them the more we do them. These ones you hopefully mostly have memorized already. To be honest, these ones don't really show up a whole lot. Like we used them today, but before today we didn't really use them yesterday. and the one that we did for number 3 and 4 is pretty much the only time you're going to use these. So what I'll say with the other ones is you should basically have these memorized, but you can put them on a cheat sheet, and worst case scenario, at the end, you can use them for a little bit. Okay, so the really difficult ones I will give to you. The ones that are harder to memorize, the easier ones you should memorize yourself. Okay? All right, so we're working on number 6. So number 7 says tan theta cotangent theta minus cos squared equals sine squared. So we're definitely working with the left side. Any ideas on a strategy we could use? Yeah, I would use sine and cos. So this is already cos. What can I do with this? So cotangent is cos over sine. How about tangent? Sine over cos. They cancel, right? So coses cancel, sines cancel. When everything cancels, do we leave a 0 behind or a 1 behind? A 1. Okay, so we leave a 1 for that. We've got 1 minus cos squared equals sine squared. Yeah, it is, right? So if we look at it, it's one of the alternate identities for the first one. So 1 minus cos squared is the same thing as sine squared. And so I can go ahead and say that this is sine squared equals sine squared. Done. All right, go ahead and work on number 8. Are we ready for number 9? Yes? Okay. All right. Number 9. So one of the strategies that I had you guys write on your notes before was to consider things that have a direct relationship with each other. So things that have a direct relationship, like in number 8, would be sine and cosecant, because you can take a cosecant, you can turn it into sine really easily, or you can take a sine, you can turn it into cosecant really easily. Squared. Another thing that has a direct relationship is cos squared and sine squared, because you can turn them into each other. So those are things that you want to consider when you're doing these problems, because they'll make your life easier, okay? So for example, on number 9, I could take the secants and I could replace them with 1 over cos. And I could do that and get the problem right, but that is the hardest way to do this problem, okay? The better way to do this problem is to think about foiling this out. Because if you do secant times secant, what do you get? Secant squared and tan squared have a direct relationship. They can go back and forth between each other, okay? So when you look at a problem, just because you can do it mathematically doesn't mean it's the easy way. Does that make sense? Okay, so let's go ahead and FOIL this and see what we get. If we do secant times secant, we already said we get secant squared. What if I do secant times 1? I just get secant. What if I do negative 1 times secant? Negative secant, okay. And if I do negative 1 times 1? Okay. So what do you guys see? Secants cancel, okay. So we have secant squared minus 1 equals tan squared, okay. And then we're thinking about our Pythagorean identities because we see lots of squareds. And we know that secant squared minus 1 is tan squared. It's just an alternate form, right? So this is the original identity. It's just another form of the same thing. So I can take the secant squared minus 1 and I can replace it with tan squared. And I can see that I completed that proof. Now, what I did on a separate sheet of paper is I did the proof the way where you take the secants and you turn them into 1 over cos. Okay? If you did it this way, you would have a fraction minus 1 and a fraction plus 1. And so first you have to get common denominators. So see that? This is me getting common denominators. This is me rewriting them as fractions with the same denominator. This is me then multiplying, so I'd have to FOIL the top and multiply the bottom. Then I converted it to sine and cosine, then I got to tangent. So you can see I got the same answer, but was it easy like the way we did it? No. Does that make sense? So mathematically speaking, you can still prove it because you're still doing things, you're still making substitutions that are true, and you're still doing math that is legal, right? Legal math moves. But because you didn't look for the direct relationship, you have a harder time doing the problem. Okay, so the easier way is to do the secant squared with that one. Okay, work on number 10. All right, so 11 is the last one I'm going to do with you, unless we get to one that makes us stuck later. Okay, so this is the last one, and then after this I'm going to have you guys just work and get as far as you can. So for this one, we've got secant theta plus tan theta and secant theta minus tan theta. So I have two ways I can see this problem going. One way is we could FOIL it out and see what happens. The other way is we could start right away with converting all of these into sines and cosines. And again, see what happens. What do you guys think you want to do? FOIL? Okay, so we're going to do secant times secant. Secant squared. And then we have secant times negative tan, which I'm just going to say is negative of secant tan. And then we have tan times secant, which is positive this time. Now it doesn't matter if you say tan secant or secant tan, it's technically the same thing. It's kind of the idea of saying xy or yx. Those are the same. So I'm going to go ahead and say secant tan, so it's the same order as the one that I wrote already. And then I have a positive times a negative, and it's tan times tan, so I get negative tan squared. Okay? So what do you guys see? The secant tans cancel. So we have secant squared minus tan squared equals 1. And so where should we be looking on our sheet? Pythagorean identities, because we got the squareds in there. And what do you guys want to do? So we could take the secant squared and replace it with 1 plus tan squared, or we could take the tan squared and replace it with secant squared minus 1. Which would you rather do? Take the tan and replace it? Mm-hmm. Yeah? Okay. So if I take the tan, I'm going to say secant squared, keep that one there, minus, and since I'm taking tan and I'm replacing it with two things, I need to put it in parentheses, because I need to make sure that that negative goes to each thing in the parentheses. So my tan is being replaced with secant squared minus 1. And then what do I do to get rid of those parentheses? Distribute that negative. So I have secant squared theta minus secant squared theta. A minus times a negative 1 is a positive 1. and the secants cancel out, and we get 1 equals 1, and we're done. Can somebody read me the original problem for 19? Okay. This might be maybe the first problem on the assignment where it's kind of hard to tell which side is more complicated because they just look completely different. So when you are doing proofs, we would consider this side to be more complicated because it has 2 terms, and this side we would consider to be a little bit less complicated because it just has 1 big group, okay? It's easier to take 2 terms and write them as something else and get a common denominator which would make them become one thing than it would be to take this particular fraction and break it apart. That would be really a complicated process, okay? So the first thing we're going to do is take the left side and use signs, get it in terms of sine and cosine so that we have like terms with the right side. So for secant, I'm going to change that to 1 over cos. And for tangent, I'm going to change it to sine over cos. And what do you notice already? It has that common denominator. So I'm going to say this is 1 minus sine, all divided by cos. This sort of situation in trig proofs is not uncommon. This sort of thing happens not all the time, but like fairly frequently. So if you look at this, you can see that like they're kind of the same, but they're kind of different. Do you guys notice that? So if I compare 1 minus sine theta with 1 plus sine theta, that's a relationship called...
Dr. Hutchinson class, may I have them out for dismissal, please?
Yes.
Okay, thank you, Ms. Rice.
Okay. All right, so this right here is a relationship called a conjugate. And the trick to doing problems like this is to take the side that you are working with and multiply by the conjugate on the top and the bottom. Okay? So we're going to take the left side and we're going to multiply by the conjugate on the top and the bottom. So on the bottom, I'm going to write this as one big fraction now. On the bottom, I have the cos, and I have the 1 plus sine, and I am not going to multiply those out because I can see that I want that 1 plus sine on the bottom when I'm done with my problem. So the reason I did not distribute the cos is because I knew that that 1 plus sine was part of the final answer. Okay? What can I do with the top? 1 minus sine times 1 plus sine. What do I get when I multiply all those out? Yeah, it ends up being 1 minus sine squared if you FOIL it out, okay? So let's go ahead and do that. Let's multiply these. We have 1 times 1 is 1. 1 times positive sine is positive sine. Negative sine times 1 is negative sine. And then negative sine times positive sine is negative sine squared. And so the middle terms cancel. So we have a 1 minus sine squared on the top. And what do we always seem to do with 1 minus sine squareds? Oh, yeah. What do we do with them? Yeah, we make them cosquareds, okay? Okay. So at this point, what do you see? Yeah, a cos on the top and the bottom can cancel, and then you're done. So the point of the problem that we see that the conjugate is going to make our lives easier is when we get to this point right up here. So when you're looking at a problem and you can see this sort of relationship right here, that should tell you to multiply by a conjugate. And the process of multiplying by a conjugate looks like this. Okay? That's a good trick for the problems. And there is one like that, like if you look down, if you look at number 28, number 28 is a very straightforward conjugate problem. See how 28 did what we just saw? So that's a very straightforward conjugate problem, okay? It doesn't happen all the time. It's not every single problem that looks like this, but when we start to get to the more complicated problems, you guys have probably noticed they're starting to get more difficult. When we start to get to the more complicated problems, this conjugate idea starts to show up more often, okay? So that's the part that we notice that tells us to do this, multiply by the conjugate on the top and the bottom. And then after that, this relationship with the Pythagorean identities always happens, okay? And so at this point, we'd be done with that one.